In this segment, I want to talk about a couple more applications of torques and Newton's second law, things like that. No real new big ideas here, but some new ideas about how to apply things we've already talked about. So let's say that I have a rope wrapped around a pulley, as shown in this picture here. We're going to make some pretty consistent assumptions about this situation when they show up in problems. And that is, we're going to assume that the rope does not slip on that pulley. If the rope is slipping and there's kinetic friction, not just static friction, between the rope and the pulley, then that's just a complicated situation that we just won't we won't deal with that in this class, right? So if we assume that the rope never slips with respect to the pulley, and secondly, that the rope is non-stretchy at all, right? So the rope has a definite length, it cannot stretch or anything like that. With those two assumptions, then knowing something about the way that the pulley is rotating tells us a whole lot about the way that the rope is moving, and if we have some object hooked to that, then how that object is moving, right? And so the point here is that if the rope is not slipping or stretching, then the velocity of this object must be exactly the same as the velocity of this rim. That the acceleration of this object must be the exact same as the acceleration of the rim of the pulley. It just kind of makes sense. How could it be anything different? And then remember that we have this set of equations that looks like this. And so with that set of equations, right, remember these equations here, they relate an angular quantity to a linear quantity, an angular velocity to a linear velocity, an angular acceleration to a linear acceleration. And so with these equations, in knowing that the velocity, acceleration, and even distance traveled for a point on the rim is exactly the same as the velocity, acceleration, and distance traveled for some object hooked to a rope, and that rope's wrapped around the rim, then using these equations we can come up with these relations. This allows us to solve a more complex set of problems that look like this. So notice in this case we have a cylinder and a hanging mass. So we're kind of combining Chapter 5 problems and Chapter 7 problems. In this case, I'm asking, what is the acceleration of the small mass if it is released from rest? The drum rotates on a frictionless axle. Ooh, this is kind of a tricky problem, but we have all of the skills we need, right? I like this problem because it assimilates a whole bunch of the skills we've already learned in this class. We're applying Newton's second law for rotations to the drum. In order to really do that, we need to understand how Newton's second law for straight line or translational motion works for the hanging mass. Okay, let's just go through our steps. First, let's draw a picture. And I'll just keep the same, we've got a picture there. I'm going to draw the same picture without the perspective. So just a straight up end view there. And we'll use little m to represent the mass of the hanging thing, and big M to represent the mass of my rotating thing. Now we have that R equals 3 centimeters. Big M, 1.3 kilograms. Little m, 0.4 kilograms. Okay, so there is all of our data. Now let's apply torques, Newton's second law for rotations, to the drum. First, we should draw all of the forces acting on the drum at the location where they are acting. Okay, well, I actually see 3 forces acting on this drum. First of all, we have the tension from the rope, right? So on the drum, the tension pulls down. Now, certainly on this hanging mass, the tension pulls up. We'll get to that in just a second. The tension pulls down on the drum. Before we draw any other forces, let's identify our pivot point. Oh boy, I mean, the drum rotates on a frictionless axle. The drawing shows the axle. I mean, our pivot point is definitely right here. Huh? So there's our pivot point. we have the tension acting right here. Okay. What other forces are acting on the drum? Well, we have the weight. Where does the weight act? At the center of gravity. Where is the center of gravity? Oh, it's right here in the center because this is a uniform drum. So the weight acts at the axle. Does the weight create any torque then? It doesn't, right? It doesn't. Because the radius that the weight is acting at is 0. So the weight creates, and by the weight I mean the weight of the drum. The weight here, we're gonna push that down the road a little bit. The weight of the drum acting on the drum does not create a torque on the drum because it's acting at the pivot point of the drum. So R is 0. How about the normal force? There's got to be some kind of a normal force from the axle, a force of the axle pushing up, otherwise the whole drum would fall. That's also acting at the pivot point. So let's not worry about that either. I think this is the only force that actually creates a torque. We could redraw our radius slightly, and it might help us visualize our angle. There is my radius. Notice the angle between my radius and my tension is 90 degrees. So let's apply Newton's second law for rotations to the drum and just see how far we get. And don't forget our definition of torque, right? Our definition of torque is that torque equals Rf sine phi. Great. I only see one torque acting on the drum. So the net torque is fairly easy to calculate here. I only have to add up one thing. We have tension. Maybe not easy to calculate. I should have said the net torque here is easy enough to write down because there's only one torque. We don't know all the numbers, so we can't necessarily calculate it yet. So it is R times F, and in this case we're using capital R for that, times my F. My F is the tension. And that's it, right? Oh, we didn't define a coordinate system, did we? We didn't define a coordinate system. Which direction should we call positive? You know what? I'm going to go ahead and I'm going to buck convention a little bit. And I'm just going to make all of the accelerations positive. It's going to save us a chance of making an error. So let's go ahead and let's make this direction positive. Okay? So we're going to make clockwise positive. Why did I decide to do that? Well, just because that's the direction of our acceleration. So let's make the acceleration in the positive direction. Now, if this was a mastering physics problem, we might need to keep that in mind when we went to actually answer the question and, look and see how, if mastering physics told us which direction they wanted positive. Maybe they're asking for the magnitude and it doesn't matter. Maybe they said, let counterclockwise be positive, in which case, we'd need to maybe shift our answer. Okay. So we've got R times T times the sine of 90 degrees, which is, of course, 1, equals I. Well, this is a uniform drum on a frictionless axle. We should look up I in that chart that I gave you. It is 1/2 mR squared times alpha. Okay. Well, right away, we can see some simplification, right? One of my r's cancels. Sine of 90 is 1. How about alpha? Let's remember our constraints for pulleys and ropes. Remember that alpha times r equals a, which means that a equals alpha. Excuse me. Which means that alpha equals a over r. So if alpha equals a over r, we can plug that in over here, and we end up with T equals 1/2 mR a over r. Notice my other r cancels, and I end up with T equals m a over 2. Okay. So we've reached a result here. We're asked to find the acceleration of this hanging mass. Well, that is this acceleration here, right? Really, this is the acceleration of a point on the rim, but since a rope doesn't stretch or slip, that's also the acceleration of my hanging mass. So here we have tension equals mass times acceleration over 2. but I don't know the tension. So I can't find the acceleration. Now, some of you at this point would be very tempted to tell me that the tension is equal to this mass times gravity. Ooh, not quite. We've solved this problem before, haven't we? In order to solve that problem, I need to sum the forces on the hanging mass. Well, let's draw a free body diagram for the hanging mass. We have tension up and little mg, or the weight, down. We can apply Newton's second law. Notice what direction I'm calling positive. I'm calling down positive here, aren't I? We need to have a consistent coordinate system if I want the A that I wrote here to be the same as the A that I wrote here. We need a consistent coordinate system, which I talked about extensively in the Interacting Objects lecture from Chapter 5. So in other words, over here, we are calling down positive. And so we have mg minus t equals ma, or t equals mg minus ma. Starting to run out of a little room here, aren't I? I can set these two things equal to each other. They're both equal to t. And I end up with and so now I'm just one step of algebra away from finishing this problem. Okay, I've simplified my algebra over here. All the required steps are still there, but I've given myself a little room here. I apologize. Now I can solve for A. I would bring all of my terms with an A to one side, all of my terms without an A to the other side. MA over 2, capital MA over 2, plus little ma equals little mg. Solving for A, I get A equals, factor out the A, divide by the leftovers, mg, little mg over big M over 2 plus little m, and I can plug in my numbers, right? I know everything here, so I can just plug in my numbers, and I get an answer, which is 3.73 meters per second squared. Okay, let's analyze that answer. Seems reasonable. If I got 13, I'd know that was wrong, right? Because if I just cut this rope, then the acceleration of this mass will be 9.8 meters per second squared. So I'm expecting something between 0 and 9.8 meters per second squared. I got 3.73. I got a positive number. I should have, right? I've defined my acceleration as being in the positive direction. I decided that before I started, so I better get a positive number, right? I like it. So this problem's tricky. It throws students off pretty bad a lot of times, right? It's tricky. But in a way, it's nothing we haven't learned before, right? We did this same problem, but with, another mass up here, right? So we had two masses connected by a pulley, and what we did, in this problem right here, so we've done this problem here. Hopefully you practiced this problem enough to where you got good at it, right? And what we did here is we applied Newton's second law here, we applied Newton's second law here, we did some algebra to get the answer. Well, shoot, our basic strategy here is just the same. The only difference is now we have to apply Newton's second law for rotations to here, second law for straight line here, do some algebra to get our answer. It's really a very similar strategy. Now, it turns out that we can solve this with a little bit less algebra if we treat the whole system as one, right? So in that Interacting Objects lecture, I talked quite a bit about how you can group objects together and treat it all as your object of interest and ignore internal forces. Or you can treat them separately, and then we have to deal with the forces that interact between them. So, in this case, if I asked you for the tension, we'd have to deal with them separately. But if all I'm asking for is the acceleration, it turns out that you can deal with the system all at once and it saves you a tiny bit of algebra. So this is a fantastic way to solve this problem. It will work every single time. I'm going to show you another way to look at it, which is maybe a little harder to wrap your brain around, but a little bit easier on the algebra. Let me erase this. I'll be right back. Same setup. Find the acceleration of the hanging mass. This time, we're going to analyze the torques on the system. Torque net equals I alpha, right? So we're going to analyze the total torques applied to the system. That's going to be equal to the moment of inertia of the system times the angular acceleration of the system, okay? So, of the whole system, right? Well, where's our rotational axis? It's still right here. That's the only point where there's any rotation happening about, right? So that is still our rotational point, our pivot point, I should say. Applied to the whole system, what forces do we have? Well, we've got weight pulling down over here. We certainly have a weight of the drum pulling down here. And we still have that normal force, but both of those are acting on our pivot point. So neither one of those will create any torque, which means that the only torque on the system is caused by this W. Well, what should we use for our radius, right? What should we use for our radius? Well, some students are tempted to think about this right here. Well, that is absolutely where the force is applied, right? But remember that we can think of, that's not correct, right? We can think of torques as being the force times the perpendicular distance to the line of action. So where's the line of action for this force? It's right here. Where is the perpendicular distance to that line of action? It's just the radius. It's just that right there, right? So even though my force is applied way down here, it's applied at a lever arm that's just the radius of my drum, because that's the perpendicular distance to the line of action. Okay, so we only have one torque. It's due to the weight of the hanging mass. The angle between the radius and the line of action is 90 degrees. Dang, this is not too bad. So my R is that. My force is mg. Again, we're still using the definition of torque here. Great. Sine of 90 is 1. So we'll leave that off. We're getting a little bit better at this. I. What is the moment of inertia? I'm going to take an extra step of algebra in here. We have two objects here. So this would be the moment of inertia of the drum plus the moment of inertia of the hanging mass. And alpha, much like it was in the other problem, is A over R. Okay. How do I know to add these? Does it depend on my coordinate system? No. Moments of inertia always add, right? There's no way that I could combine two things and the two things together were easier to move than the one thing on its own. We always add moments of inertia. So let's plug those in. We're just going to go look those up in our chart. So we have R times little m times G equals, well, the moment of inertia of the drum, we had that last time. That's 1/2 mR squared. The moment of inertia of a mass, a point mass. This is really like a point mass. All of the mass is moving at the same distance from the rotational point. So we should treat this like a point mass. What R do we use? Again, we don't use this distance here. That would seem to indicate that the longer this fell, the greater the radius is. It's not, right? If this is way down here, if I just drawn my mass down here, it doesn't change the torque applied to here. It doesn't change how it's going to speed it up, right? So indeed, it is just this R right here that we're going to put into the point mass equation for the moment of inertia. And so this is little m R squared times A over R. Notice that this R cancels with one of those R's. This R cancels with the other of those R's. And when we solve for A, we get A equals mg divided by big M over 2 plus little m. And you will notice that that is the exact same result we got doing it the other way. And we could plug in our numbers, we get the same number too, right? So our algebra turns out the same result. I personally think this is the superior way. It's easier on the algebra. It's a little harder to wrap your brain around. What's harder about it? This business of ignoring internal forces, right? I've been preaching about how we can't just let the tension equals mg. That's still true, but if we're treating this whole system, then the torque is just the weight, right? And we ignore internal forces at this point. Since we're treating the whole system, the tension is an internal force. The other part that's tricky for students is this business of being sure to include all of the different parts of the system. So we just spend a little while talking about these constraints due to a rope around a pulley and how they give us these relationships between some linear quantities of falling mass and some rotational quantities, how that wheel that we've wrapped the rope around rotates. We get a similar sort of effect with a rolling wheel. So here's a picture of a rolling wheel here, and this has two lights, a red light near the rim and a white light in the center. And so we see this very interesting pattern here, that this path right here that the red light takes, this is the path of an edge, of a point on the edge of the wheel, right? It does this kind of woo, woo. It turns out the shape of this is called a cycloid. Trivia. Won't ask you about it. The center of the wheel just keeps on moving, right? And so we get very different motion depending upon the point that we're in, right? You know, and it's kind of interesting. This red light has some breadth to it, right? And so, you know, a point right on the very edge has a more extreme sort of M shape than a point that's closer to the axle, right? Which is going from here to here. You know, a point on the rim is going all the way from there to there, right? So every point on the wheel follows a slightly different trajectory. We started out Chapter 7 by talking about how, in general, motion can be modeled as a combination of linear motion, or translational motion, and rotational motion. And so we can understand this motion in the same way. The center of the wheel always moves along at v. That's just how fast the wheel is moving, right? If you were driving your car, this v right here would be the speed that your speedometer reads, right? So I'm going 60 miles an hour down the road. That means the center of my wheel is going 60 miles an hour. Now, if I wanted to know what about the speed at some point on the edge of the wheel, then that would be a combination of the rotational motion and the translational motion. So every point on this wheel is headed to the right at speed v. In addition, the wheel is rotating. So every point on the wheel is heading to the right at a speed v. In addition, it is rotating. It is rotating. And since it's rotating without slipping, then we can use the relationship that v equals omega r. And so that's why we say that the top is rotating with speed omega r to the right. The bottom is rotating with negative omega r to the left, right? So we've got translational motion plus rotational motion equals the speed of any given point, right? So in the center here, let's look at the center. That's probably the easiest to understand. It's going to the right, translational motion, v. Nothing in the rotational world, because it's right at the pivot point. Therefore, its total speed is just v, same as omega r. A point up here on the top has a velocity v to the right. A rotational motion of v equals omega r, also to the right, right? Now, this is v and omega r, both exactly the same because it's not slipping. That means that its total motion is twice as fast. How about the bottom? V to the right from translational, v to the left from rotational, it's not moving at all. So you're driving your car down the road at 60 miles an hour. The top of your wheel is moving at 120 miles an hour. The middle of your wheel is moving is moving 60 miles an hour, and the bottom of your wheel is not moving at all because it's in contact with the pavement. And it's not slipping, right? So it's kind of weird to think about. But the bottom of your tire is not slipping. So every time your wheel goes around, right, it's going from 0 to 120 miles an hour back to 0 every time it rotates. There's some pretty crazy acceleration happening if you imagine a point right on the edge of that wheel. You know, if we had some point, I don't know, right here, let's say, and I wanted to know what so it's not in the center, and let's say that I wanted to know what the velocity is at that point, of that point. So what's the total velocity of that point? It's not one of the ones given on the slide. It's a little bit more complicated of a situation. Well, let's say that the wheel is rotating in that direction. Okay, well then this point is going to be the combination of the translational motion and the rotational motion. Well, the translational motion just looks like that. What about the rotational motion? Well, it's rotating like this, so it's going to be going upwards, right? If it was a point right on the rim, it would be going V, right? But it's not on the rim, it's closer to the center. And remember that V, the velocity of a point on a wheel, is equal to omega times r, you know, so let's say that this is halfway between the edge and the axle, in which case this would be V over 2, right? And so we've got right there. This is the translational component, and this would be the rotational component. So what is the total velocity? Well, we'd want to move this over here, so we're adding our vectors tip to tail. And our total velocity would be right here. Again, for one specific point on the wheel. A point that's neither in the middle nor at the edge. Okay.